Hello there. This lecture is all about the sampling distribution and the standard error. So in the past, we've been working with population distributions and sample distributions, which are basically just the visual representation of the frequency or how many times specific scores occur in either a sample or a population. Now we're moving into situations where we're looking at all the possible sample means that could be drawn from a single population, and the visual representation of how often those means would be expected to occur just due to chance is the sampling distribution. Now, in the past, we've used the standard deviation as our measure of spread or how consistent scores are, or on average, how far scores tend to be from the mean. Well, now we're going to be using the standard error as our measure of spread of how far most sample means tend to be, just due to chance. If you took every possible sample mean from the population, how much of a difference you'd expect to see between any given sample mean from the population and the population mean just due to chance. So we're not looking at scores anymore. We're looking at sample means, and the population mean is still going to be kind of our midpoint, what we're comparing our scores to. And we're done with the standard deviation for now. We're not looking at the spread of scores anymore. We're working with the standard error, which is the spread of means. So this lecture will really just introduce you to what that distribution is, how it's constructed, some rules that apply to that distribution, and then looking at the standard error specifically. And in the next lecture, I'll show you some practical tools that you can use with this distribution to make decisions in the workplace. So I'm going to start this lecture by looking at how the sampling distribution could be conducted or created using a very small population and a very small sample size. Now, don't panic while I'm doing this demonstration because it is a little bit confusing, and I'm never going to ask you to do this on your own. I'm just doing this to simply help you understand where all those scores that we're going to be looking for in the sampling distribution come from. Then I'm going to go into the three tenets of the central limit theorem that give us some rules about that distribution that prevents us from having to do the thing that I'm going to demonstrate when I'm demonstrating the sampling distribution. Then we're going to look at the impact of the standard deviation and sample size on the standard error. Basically, the more spread out your original scores are and the smaller your sample size, the more error you're going to expect. But we'll get into the nitty-gritty of that in a little bit. Then I want you to visualize the population distribution with scores versus the sampling distribution with all possible means that could be taken from that population. So I'll draw that out and show you how now the standard error dictates how spread out that distribution is, or how fat the normal curve is when we draw it out. Then I'll just summarize the terminology covered in the lecture and summarize all the different distributions, population, sample, and sampling distributions that you have covered so far this semester. So for any given population, there are typically a huge number of samples that can be drawn from that population. Normally, one thinks of sampling from relatively large populations. Remember, just populations are everybody or everything that the researcher is actually interested in, but oftentimes we don't have access to the entire population, so we'll take a sample to study a population. But luckily, even though we typically work with really large populations, the concept of sampling distribution can be illustrated with a very small population, in this case, a population that just has 3 scores in it. So for our purposes, we're going to assume that the sampling distribution we're going to look at is based on random sampling with replacement. So for instance, after you select one value, that selection is replaced before the next selection is made. So technically, you could select the same value twice. So you see our sample size is 2. So this table represents every single possible 2-number combination that you could have gotten from this original population. So because it's random with replacement, we could get a 3 and a 4, or we could get a 4 and a 3. Same 2 numbers, just drawn at separate times. So this is the simplest distribution to work with. Although random selection with replacement is not super common, when you have a large population, which you do in most cases, not for this demonstration, but in real life, this distribution works the same way, even if random sampling is not with replacement. So if your sample is relatively large compared to your population and you use random sampling without replacement, there's minor corrections that can be made in your formulas to compute the standard error, but we're not going to worry about those situations in this class. That's for more advanced statistics.
So again, as you can see in the table, every single possible random sample of 2 with replacement from this population of 3 scores is represented. The first and the second score you see, the first and the second x values are represented here. Then you're going to see in this column, the mean for each of those potential samples are here. Now remember, this doesn't represent specific samples a researcher took. It represents all possibilities, or in other words, all possible samples and their means. So these means can be transformed into a frequency distribution table that you see here. So you'll see that here's the mean values that we got, right? Then you'll see how many times those values appeared. So how many 5s do we have? We have 1 5. How many 4.5s do we have? 1 2 4.5s. How many 4s do we have? 1 2 3 4s. Then you'll see we have 2 3.5s and 1 3. And that's where those frequencies come from. Then this p-value just tells you the probability that if you took a random sample of 2 from this population, what's the probability that they would have a mean of all these values? So this tells you basically there's 11.1, if we multiply it by 100 to get a percentage, 11.1% chance that if we randomly took a sample of 2 from this population, that mean would be a 5. This one, right? There's a 22.2% chance that if we randomly selected 2 people or 2 scores from this population, that they would have a mean of 4.5. Now, in future lecture, we're going to look at determining probabilities of specific samples using the unit normal table, but we're not there yet. Now, I really want to point out that this table is then going to be represented into this beautiful graph right here. So this graph represents every possible sample mean, right? They could have been coming from 2 scores from that population. And this section right here represents how often that occurred, how often we would see those potential sample means from the population. So you see here, right? A score of 4. There's 3 possible times that you would get 2 scores with a mean of 4 from the population, and you see that that's the frequency here in the graph, just in case you forgot how those graphs work. Now, I said this earlier, but I want to say it again. Do not worry about constructing one of these on your own. This is a demonstration to help you understand the contents of the sampling distribution, right? It's every single possible sample mean of a specific sample size that you could get from the population. For now, I just want you to focus on understanding that concept and this sampling distribution graph that again represents every possible sample mean of this sample size too that it could have been drawn from the original population. So now let's take a look at the mean and the standard error based on this sampling distribution. Again, you're not going to have to calculate it this way. I'm going to introduce you to something called the central limit theorem in a minute. It's going to prevent you from having to do this, but it's important for you to watch this slide so you can understand the concepts behind where these values come from. So again, we've got each possible 2 sets of scores or 2 values from a set of 2 that could be drawn from this original population and the mean, right? So 3 plus 4 divided by 2 is 3.5, for instance, right? 3 plus 4 divided by 2 gives you that mean of 3.5. So the mean of the sampling distribution, if we are drawing it in a normal curve, the thing that goes right in the middle, right here, that is always going to be equal to the original population mean. So check it out, right? If we add all of these means together, we get 36. We divide that by the fact that we have 9 samples, right? That's right here. And we get a mean of 4. So the mean of all the possible sample means is equal to the original population mean. That always works that way, which is awesome because if we had a population of 100 and a sample of 30, imagine the pain that would be caused by trying to figure out every single possible 30 number combination from 100 numbers to then get all the means and then figure out the mean of those means. It's always going to be equal to the population mean. Oh, happy day. Okay, now let's take a look at the standard error. So I went over how to compute the standard deviation in a previous lecture and looking at sum of squares and all those things. So the way that you could do that here is with this formula. Again, you're never going to have to use this. I have a very simple formula here, but just to demonstrate how this works. So here you've got the sum of squares divided by the total number of samples. Well, at this point, we know we have 9 samples, but we don't know what this sum of squares value is, so we use this formula. Similar to the one that you've seen in the past with sum of x squared minus sum of x quantity squared divided by n, but now the x's are replaced with means and the n is replaced with number of samples. So to get this 147, I had to square each mean, because order of operations tells me I have to solve for the exponent, square each mean, then add them together. So I would square each mean. You see 3.5 squared is 12.25, 4 squared is 16. Then you add all those squared means together to get that 147. And then this part, you just add all the means together first because it's in parentheses, so that comes first, 36. Then you square it. And then down here, we still have our number of samples, 9. So this becomes 147 minus 36 squared is 1,296 divided by 9 equals 147 minus 144 once you solve for that fraction, and you get a sum of squares of 3. Then you plug that 3 into your standard error formula, do some division, take the square root, and you get a standard error of 0.577. So what this tells me is that just due to random chance, I would expect that any given sample of 2 scores taken from this population would have a mean that's about 0.577 points away from the population mean. Now, if that didn't make sense, that's okay. We're going to talk about the standard error quite a bit in this lecture, but just to give you a rough idea, this tells you the difference you'd expect to see between any given sample mean and the population mean just due to chance. Now, luckily, this formula, number 1, would require us to do this process here, to take every single possible sample of a specific sample size from a population and then calculate all the means and work with those scores. Thank you, statistical gods. We have this formula, which is the standard deviation for the population divided by the square root of the sample size, not the number of samples, but the sample size. So here you will see our population standard deviation is 0.816. That's where this guy comes from down here. And our sample size is 2 scores. So that's why this says square root of 2. Solve for the square root, you end up with 0.816 divided by 1.414, and voila, you get the same standard error that I got using this unbearable formula, especially with larger samples. So again, luckily, you do not have to figure out every possible sample of a specific sample size that could come from the population to construct and understand a sampling distribution and to calculate the mean and standard error. Think about this down here. So the number of possible samples that you could get is equal to the population size to the power of the sample size. So that's what this represents right here. So you can see that doing what I just demonstrated with larger populations or samples would be a nightmare. Think about this. If your sample size, or if your population size was just 20, which is really small in the real world, and let's say that you were taking every possible sample of 5, that would equal 3,200,000 possible samples. Anybody got time for that, right? We're not going to try to sit down and figure out every possible combination, and we have 3,200,000 possible combinations, possible samples right here. Yuck. So what I'm about to introduce you to, something that actually guides these easier calculations. I'll highlight them in purple, because purple is a happy color. The easier things that I just showed you, it's called the central limit theorem, and that is the theorem, the set of rules that prevents us from having to go through all of this. So the central limit theorem makes it possible to understand the characteristics of the sampling distribution, or the distribution of all possible sample means, without taking hundreds or thousands or millions of samples like you would have to do with realistic large populations. So the central limit theorem identifies the three basic characteristics of the sampling distribution: shape, central tendency, or the mean, and variability, or the standard error. So if we look at this, when it comes to shape, the shape of the sampling distribution, and that's just really like, is it a normal curve? Is it skewed? When we sketch it out in that graph, what does it look like? Depends on two factors. So the first factor is whether or not the population distribution is normal, and also the sample size. So the shape of the population from which you sampled could be an issue if your sample size isn't large enough. So normally distributed populations, scores that are in the population from a normal curve in a frequency distribution graph where most values in the population are in the middle with some extreme on high or low ends of the distribution. If you have a normal population distribution, then the distribution of sample means, or the sampling distribution, will be normal regardless of sample size. Even if your sample size is just n equals 1, the sampling distribution of the mean will be normal because it'll be exact copy of the population distribution. And again, a normal distribution just looks like this. Oh, we're still using purple. How cute. All right. Also, you see there the sample size. So if the population from which you sample is extremely non-normal, the sampling distribution of the mean will still be approximately normal given a large enough sample size of about 30 or more. Greater sample sizes help ensure that the sampling distribution of the mean is approximately normal. So if you start off with a population that kind of looks, blah, it's all over the place, or it's got a really big negative skew or a really strong positive skew, once you take a sample size of at least 30, and then you plot all the possible means that you could possibly get right there, you're going to get this beautiful normal curve. And that's because you're getting more similarities in your means where they're going to kind of stack up in the middle because you have more scores used for each of those means. It's not important necessarily that you understand why it happens, just the criteria for when it happens. So again, just as a recap, if you have a normal shaped population, looks like this, your sampling distribution will be normal no matter what. But if you do not have a normal population distribution, as long as you have a sample size that's 30 or more, you're still going to have that normal shape. Now, this is especially important because Excel is only able to estimate probabilities of samples based on only the population mean, population standard deviation, and sample size if we are working with a normal distribution. So although we're not looking at probabilities just yet, that's going to be down the road, it's important to realize that it's a really good thing that we almost always have a normal distribution, and we'll always have one if our sample size is large enough, so that we can use tools based on statistical values to figure out probabilities and proportions. Like how likely would it be to get a mean of this value, those things. All right, next. And there's our thing, right? You can't determine probabilities without raw data unless you have a normal distribution. So central tendency is the next thing I want to talk about that central limit theorem covers. And that's just, again, like I demonstrated earlier, the mean of the sampling distribution is always equal to the population mean. So if you take all the possible means and then add them together and divide by how many samples you have to get the mean of all the possible means, that's unnecessary because it's always going to be equal to the population mean. So when you're sketching these distributions, you can just put the population mean right in the middle of your normal curve. Now, although applying the concepts of z-scores, if you remember from a previous lecture, and probabilities, which we'll get to eventually, although applying those concepts of z-scores and probabilities to single scores is great for the illustration of these concepts, in actual research, we rarely care about single scores, or in other words, a sample size of 1. We care about samples. A researcher is not going to take a sample size of 1 to study anything. They're going to try to get as big of a sample as possible to approximate or estimate what would actually happen in the population if they had access to everybody or everything they wanted to study. So now, as I said earlier, instead of working with the standard deviation, which is the average distance between all scores in the mean to determine variability, we will be working with the standard error, which is the average distance between all possible sample means of a specific size and the population mean. So the problem with samples is that samples are variable. They have different individuals, different scores, different sample means. Thus, sample means often differ from the population mean just due to random chance, just naturally occurring differences. If you look at that distribution, the normal distribution, right? Just due to random chance, A lot of your means are going to be close to the original population mean, but there are some extreme values here and here that could happen just due to random chance. And the extent of the differences we expect to see due to chance, if we kind of shade in the middle here, like what's the most common difference, the typical spread of means from the population mean, that is your standard error. And that's just a measure of sampling error, which is the discrepancy between sample statistics and population parameters. So again, the standard error tells you the difference to expect between the mean of any given sample of a specific sample size and the population mean just due to chance. And it is a very important concept for the sampling distribution. So just to recap, it's the standard typical distance of any possible sample mean from the population mean. And there's a simple formula for computing it right here, assuming you have the population standard deviation given to you. And what this really tells you is how well should any randomly selected sample mean of a specific sample size estimate the population mean? How much error do you expect in, what you're trying to measure in the population based on a sample? Also, how much of a difference between the sample mean and the population mean you would expect to see just due to chance? And if you think about this, a large standard error means that the sample means are scattered over a wide range. So there's big differences between different sample means. So if you think about if we drew it out, this would be a situation with a larger standard error. It's a fatter curve. There's a big spread in all the possible means you could get. Whereas a smaller standard error means that the means are really close together. So you would expect that any given sample mean that you would take from the population would be a pretty accurate representation of the population. So that would kind of look like this, right? Where most scores are really close to that mean in the middle, whereas a larger standard error, they're more spread apart. There's more differences expected due to chance. So as you may have guessed, based on the formula for the standard error, the value for the standard error, or the amount of differences you would expect to see just due to chance between any given sample and the population, depends on how spread out scores are in the population, or the population standard deviation, and your sample size. So let's think about this mathematically. If you have a larger value in the numerator of a fraction, you're going to have a larger value overall. But if we think about this conceptually, if you have more differences, more spread in your scores in the population, then you're going to expect more differences just due to chance. Because if the scores are all spread out, then your means from those scores are also going to be pretty spread out. So let's think about this in a practical example. If you're measuring the salary of Wal-Mart cashiers, you would expect to have less variability or differences in salaries than if you were measuring the salary of all Walmart employees, right? Cashiers have the same position. There's going to be less variability in their salaries. But if you look at the salary of all Walmart employees, it's going to be all over the place, big differences. So the standard deviation for salaries of Walmart cashiers would be smaller than the standard deviation of salaries for all Walmart employees. So given that, you would expect less error in estimating the salary of all Walmart cashiers based on a sample, right? Because you've got a small spread. And any given random sample of Walmart cashiers would probably give you an accurate estimate of the overall salary of Walmart cashiers. Because again, there's not a great deal of differences in salary between them. There's a lower standard deviation, less spread in scores. So that's going to give you a lower standard error, less differences between any given sample mean and the population mean. And so you would expect that your sample would be a more accurate representation of the population. Or in other words, any given sample mean would probably be a pretty close approximation to the population mean. But if you were trying to use a sample of Walmart employees to estimate the salary of all Walmart employees, there would probably be a great deal of error in your estimation because there's tremendous differences in salaries across the multiple positions at Walmart, with a few outliers who make much more than other Walmart employees. So think about it. In the population, there's a CEO, there's an optometrist, attorneys. So there's a really high standard deviation and a higher standard error because that sample is not expected to be a very accurate representation of the population, right? Any given sample that you would take probably wouldn't include that CEO or that optometrist because there's so few of them. So you'd expect your mean to be really far off in the sample from the population mean. Now let's take a look at sample size. So if you were measuring the salary of all Walmart employees, you would want as large of a sample as possible to capture that full range of salaries for positions across the Walmart hierarchy. So you'd have more chance of getting those really high paid employees in your sample. So you'd have a more accurate assessment of how spread out the salaries, how different the salaries are. So that larger sample size gives you mathematically a larger denominator in your fraction, right? So if you have a larger denominator, you're going to have a smaller value overall. And again, conceptually, if you have a larger sample size, you're expecting to have a more accurate representation of the population and you're expecting less error. If the math thing is confusing to you, think about this. If we talk about the standard deviation, if we have 10 divided by 5 versus 100 divided by 5, well, here we have a larger value, so the overall value is going to be larger than when we have a smaller value, we're going to have a smaller overall number. But if we think about the sample size in the denominator, right? If we have, let's see, 10 divided by 2, right? We're keeping the numerator the same, just a different denominator, a different sample size. If we have a smaller sample size or a smaller denominator, we're going to have an overall larger value. But if we have a larger denominator, we're going to have an overall smaller value. So just to demonstrate the mathematical reasons for how the standard deviation and the sample size impacts the standard error. And again, conceptually, bigger spread in scores, bigger spread means more error. Smaller sample size, less accurate, more error. Larger sample size, more accurate, less error. So for me, the best way to make sense of the sampling distribution and kind of what it tells you about these scores or means is to draw things out. For the rest of this lecture and for following lectures, we're focusing on normal distributions. So for the population distribution of Walmart salaries for all employees, we'll focus on it being normal, which it probably is pretty normal. Most things are. And we're going to draw our normal curve. And we're going to plot our population mean right in the middle. So that would be our 60,000. I'm just going to put 60K to shorten it. And if you think about this, remember, going back to mean and standard deviation, most salaries are going to fall within one standard deviation of the mean. So if we have X values here, and I'm using X because we're looking at the population distribution, which includes scores, not means, then we have z-scores here, right? So remember the z-score for the mean would be 0. 60K is 0 standard deviations from the population mean. And most salaries are within one standard deviation of the mean or have a z-score between -1 and +1. So if we take 60,000 plus the standard deviation of 30,000, we get 90,000. So it'll be about here, 90K. And if we look at the low end, right, if most scores are within 30,000 of 60,000, or in other words, most people's salaries at Walmart are within $30,000 of 60,000, then our low end would be 60,000 minus 30,000, and we would get 30K here. So based on this data, we know that the majority of employees at Walmart make between 30,000 and 90,000. It's a pretty huge standard deviation there. Again, because there's people at the low end and the high end. Now, technically, this should be as big as this, but I'm not the best artist in the world. But you get it. You get an idea. All right. So now let's take a look at the sampling distribution. Notice that the mean of all possible sample means is equal to the population mean. So I'm still using the population mean for my sketch. So now we're looking at, for any given random sample of 100 employees, you would expect their mean salary to be within $3,000 of the actual population mean, right? Because this is our standard error. So now we're not talking about scores anymore. If we were just randomly taking a person from the population, we'd expect their salary to be between 30 and 90,000. But now our error is much, much smaller, right? Because now we're looking at a sample of 100. We're going to expect more consistent sample means with 100 people because we're going to have more information from the population, people with higher and lower salaries in the sample, than if we were just looking at a single person from the population. So now when we sketch this out, the width of our graph isn't going to be dictated by the standard deviation. It's going to be dictated by the standard error. And I'll show you in the next lecture, you're going to be looking at z-scores more, but just as a preview, your z-score of 1 isn't going to be 1 standard deviation above the mean. It's going to be 1 standard error above the mean. And your z-score of -1 isn't going to be 1 standard deviation below the mean. It's going to be 1 standard error below the mean. So with that being said, I want you to pause this video, bust out a piece of paper, and draw what you think the sampling distribution is going to look like, using kind of the same strategy here, but instead of using the standard deviation, use the standard error. Okay, hopefully you did it, because practice makes perfect. So now I'm going to draw this out for you. I'm going to strategically make this curve skinnier because our level of error is much lower now, because now we're not just taking a single score from the population, we're taking population or sample means of 100. We're still going to pop our population standard deviation right here in the middle. Because remember, the mean of all possible samples is equal to the population mean. Now we've got our standard error of 3,000. So when I look at this, and this is going to be x bar now, not x, because we're talking about sample means in a sampling distribution. We still have our z-scores though. The z-score for the sample mean is still 0 because 60,000 is 0 standard errors away from 60,000. And if we go z-score of 1 and z-score of -1, 60,000 plus 3,000 is 63,000. So this would be 63K. And 60,000 minus the standard error of 3,000 is 57,000. So now, for any given random sample of 100 employees, you would expect their mean salary to be within $3,000 of the actual population mean, or between 57,000 and 63,000. In other words, if you were trying to estimate the mean salary of all Walmart employees, your estimation would be expected to be off by about 3,000. So this was super conceptual. So I just want to quickly recap the most important terminology and then the different distributions that have been discussed throughout the semester and in this lecture. So the first thing is the sampling distribution, which is also called the distribution of sample means. Those two things can be used interchangeably. And remember, it represents every possible sample mean of a specific sample size that could be drawn from the population. So remember, all those possible sample means are represented along this x-axis, and then how often you would expect those means to occur would be represented along the vertical or the y-axis, the frequencies. Now, the mean of all possible sample means, right, the thing in our normal distribution that goes in the middle, is equal to the mean of the sampling distribution, which conveniently is equal to the population mean. Hooray. So we just still put the population mean right in the middle. So this is really just saying what the expected value of the sample mean would be if the sample is an exact representation of the population. And it would be the most common sample mean value that could be found among all possible samples from that population. Remember, most common, highest frequency. So on average, your sample means will be close to the population mean, but not always. The standard error, our new measure of variability. It's the typical difference between every possible sample mean and the population mean. So just due to chance, here's how much of a difference you'd expect to see between your estimate based on the sample and then the actual value in the population. So what it really tells you is how far away you expect any randomly selected sample mean to be from the population mean just due to random chance. This is going to become pretty critical in the next lecture where we're talking about, okay, we took a sample, we did something to them. Now we want to see if the reason they no longer represent the population is due to sampling error, right, just due to chance, or if we can be confident that their difference is much larger than the difference we'd expect to see due to chance. And whatever we manipulated or did to that sample is the reason we saw that difference. So that is where we're headed next. So if the sample represents the population fairly well, or in the next lecture, if whatever you did had no effect, then the sample mean should be within one standard error of the population mean. So between a z-score of -1 and +1. Now, finally, I just want to recap the summary of all the distributions that we've pretty much covered so far. And remember, distribution is just a fancy way to say how often all the scores or means that we're looking at occurred, right? So distributions is just kind of like if we have a frequency distribution table, we've got X and F, each score, how many times they occurred, or each mean and how many times those would occur. And then we could put those into a nice, beautiful graph where X or the mean is represented here, all those values, and then the frequency is here. So let's first look at the contents. So in the population distribution, we're looking at scores, X values, from all individuals in the population. And in the sample distribution, it's the same thing. We're looking at all possible scores or X values from individuals in a single sample. And again, remember the population is just everybody or everything the researcher cares about. And then typically you don't have access to all that. So you take a subset of that population and study it, and that's your sample. Now, the sampling distribution or the distribution of all sample means, not scores, means of all possible random samples of a specific sample size, or N, taken from the population. Now, if we look at shape, the population and sample distribution can be any shape. Oftentimes in the population it's normal, but it could be really any shape. But remember, central limit theorem tells us that in the sampling distribution, it's either normal if the population distribution is normal, or if we have at least 30 scores. So think about the criteria that would have to happen for us not to have a normal distribution in the sampling distribution. Well, we'd have to have two things happen. We'd have to have a non-normal population distribution and fewer than 30 scores. All right, the means, right? So here's your population mean. Here's your sample mean. Basically the same exact thing. You add up all the scores, divide by how many scores you added, just different notation. And then remember, for the mean of the sampling distribution, there's computations involved, but we can just default to what the original population mean was, because it always is equal to the mean of all possible means, thank goodness. Then let's finally look at variability. Variability is just a fancy word for spread, differences, dispersion, how consistent things are, variability. So in the population and the sample, we look at the standard deviation. In the population, it tells us the typical spread of population scores from the population mean, and in the sample, you basically have the same exact thing. You just replace the word population with sample. The typical spread of sample scores, right, X values, from the sample mean. Now, our measure of variability is the standard error, which is the standard deviation of the sampling distribution, which is what I demonstrated at the very beginning of the lecture with that crazy table and all those possible samples. But we're calling it is the standard error. And it's the expected difference between a randomly selected sample mean and the population mean just due to random chance, naturally occurring sampling error. And again, this is very important to researchers because they will take a sample from the population, do something to them, and then they can't just assume if there's a difference in the sample that it's due to what they manipulated. They have to compare that actual difference to the difference they'd expect to see just due to chance or the sampling error to see if they can be confident that the differences they observed are due to what they manipulated or what they did in that sample. So I hope this summary helps you kind of see where we've been and where we're headed and where we're going to stay for a little while, and that you're feeling pretty confident about the concepts behind the sampling distribution and the standard error because you will be using those in the future.